Welcome to Mr. Hobbs A.P. Chemistry class. This is Thursday, January the 5th, 2017. Feel free to subscribe to this channel. Today we're talking about thermodynamics, reviewing enthalpy, talking about entropy and Gibbs free energy. So, given this graph, how much energy is needed to vaporize 88 grams of CO2? Knowing anything and everything about CO2, what's the molar mass of CO2? 44. No, it's right there. Okay? That way it's not following. Okay? 44. So 88 grams obviously then is?
2 moles.
So we have 88 grams. Now, CO2 times 1 mole over 44 grams. Okay, so that basically is 2 moles. So then what do I do with that? By 10. Okay? 10 kilojoules per mole. Try that. Do it right. Okay? I knew I was messing up because units weren't canceling out. Okay? So doing crazy math in your head, 88 divided by 44 is 2 times 10. Looky there. 20 kilojoules. So what does that mean? What's it going to do? What does that 20 mean? What is that? What did we just find? Okay, so the CO2 is already at its boiling point. But we have to put in another 20 kilojoules just to get it to turn into CO2 gas at its boiling point. Temperature didn't change at all. That's just what type of energy is this? Kinetic or potential? It's all potential energy. It's latent. That's why it's constant temperature. Changes in potential energy. So that's 20 kilojoules of potential energy that's added into the CO2 to change it from a liquid to a gas. Okay, now CO2, just FYI, CO2 doesn't normally go through the liquid state. It normally goes straight from the solid to the vapor, and we call that sublimation. So we could find the heat of sublimation as well, just figuring out how much energy it took. Now, why is there more energy needed here at 250 at point D than point B? Okay, whereas when you're here, what are we doing? We're simply going to have to be able to move apart. So in a liquid, are they completely separated in the liquid state? No, all you got to do is stretch and bend the bonds there. But to make it go to a gas, then you have to break them completely apart from one another. And so as a result, it takes a whole lot more energy to vaporize something than it does to melt it, because you have to completely break the bonds apart from one another. Okay? So, it is always going to be a higher heat of vaporization than it is going to be the heat of fusion. Now, what about the slope? Why is the slope of C flatter than the slope of A? The specific heat is lower for which one? Okay, I've heard both. How many think A? How many think C? How many don't think? Okay, that was the majority. Just for those of you viewers, you thousands out there. And so, again, we're buying degrees. Since this one is going up slower, what does that mean about the amount of energy it's requiring to do the change? It takes more. So it's going to have a higher specific heat. The flatter the slope, the higher the specific heat, which means it takes more energy to cause a given temperature change. The steeper it is, means that we're going to have less energy. Okay? So this is CO2. If I put something like gold that had a specific heat of 0.129, that's joules per gram, okay? but it's going to be a very low specific heat. Let's say it's less than this. What's going to happen then to the slope of A? It's going to be steeper. If we put something that's going to have a higher specific heat than CO2, then it's going to be flatter. Okay? Because it takes more energy. The more heat it takes, the slower the temperature is going to go up. So we need to be able to understand the relationship between specific heat and temperature change. The higher the specific heat, the less the temperature is going to change.
So does the liquid state require more specific heat than the gas?
I don't know if I can say always. All I know is water is the most common one, and for water it does. And I made this one up for CO2, so I don't know if it's really true for CO2 or not. Okay? Probably is. And then lastly, why is the heat of vaporization of CO2 so much less than water's if water's is given as 40.6? 10 compared to 40.6. Versus, what do we know about anything and everything about CO2? What do we know? It's nonpolar symmetrical, therefore what's the only type of attractive force? Weak London forces. Whereas water, it's polar, it's going to have all three. It has London forces, dipole-dipole, and most importantly it has hydrogen bonds. So it's attractive forces, and really, I mean, that's probably what I would say if I was trying to answer this in a short answer question. I would say that CO2 is a symmetrical nonpolar molecule, only has weak London forces, whereas water is a polar molecule that has hydrogen bonds between its molecules. As a result, the IMFs between water are much greater than between CO2 molecules. Thus, it requires much more energy. Now, this was in a multiple choice question, so then you just find the multiple choice answer that best says that in a concise way. Okay? They probably would just say water has stronger IMFs or intermolecular forces than CO2 does. Okay? So we're good there? We understand? This graph, again, has been on the last 2 years AP. So probably need to make sure we understand it fully and can interpret it and know everything that we're talking about on this. So yes, when we have a test on this, most likely you need to be able to answer questions about it. All right? So that kind of finishes up chapter 5. That finishes up everything about enthalpy. Okay? Now we need to go in and talk about, so far, and if you recall, if you go all the way back to the beginning of the notes on this, I said that there were two driving forces, two things that cause chemical reactions to occur. And the first one was lower enthalpy. And everything that we've been talking about so far has been enthalpy, the change in heat at constant pressure. Everything in nature always wants to get to the lowest possible potential energy state. That's the first driving force. Now we need to talk about the second one. So this is going to be a big 2. Number 2, our second driving force is entropy. And we use S, and I have no idea where the S comes from, but we use S for entropy. I think they just ran out of letters, and they just had to randomly pick one. H is enthalpy, well, because it's heat. Okay? We have delta E for energy, just the overall energy, and the delta E, again, is the total internal potential and kinetic energy. It's all of your energies combined. There's no way for us to know in this piece of paper what all of the different factors are because the electrons are constantly moving and shifting. There's electron-electron repulsions that change. There's There's all the bond potential energy, the kinetic energies. There's just way too many factors going. There's no way we can know how much energy is in this piece of paper or in anything. Okay? So we only can measure the changes in energy. And when those changes in energy occur at constant pressure, we say that then that change in energy and the change in heat is going to be about the same thing. If you want to read the beginning of chapter 5, it goes into an explanation of the energy is really Q plus W, the work. The work is P delta V, the pressure times the change in volume, but the change in volume is usually pretty negligible, and so therefore the work function is negligible, so delta E is equal to Q, and so Q at constant pressure we call enthalpy, so the energy and the heat we're saying are basically the same thing. I'm sure you followed all of that. The point is that we can only measure changes in heat, changes in energy. But with entropy, we can actually measure the absolute entropy. Notice it's not delta S, it's just S. So entropy, does anybody know what it is a measure of? It's a measure of the disorder. A quantitative measure. Of the disorder of a system. Okay? Now, the first law of thermodynamics is simply the conservation of energy. Energy is neither created nor destroyed, it just changes phase. And put that mathematically, we say Q lost equals negative Q gained. The reaction loses heat, something else is going to gain heat. Okay? So, that's the first law of thermodynamics. Entropy principle is the second law of thermodynamics. Okay? And this is the key, and I don't know where we are, so I'm just going to use bullets. And so, in nature, reactions tend towards the highest entropy. In other words, a positive delta S. So our second driving force is that things want to go to a higher entropy. Everything drives to a lower energy, but everything in nature drives to a higher entropy. Now, in a particular system, entropy can both increase or decrease. We can freeze water. We can make water go from a liquid to a solid. That's going to have lower entropy. A solid is much more orderly than a liquid is. So a liquid has a higher entropy than a solid. But we can make water freeze and become a solid. But in doing so and putting it into our freezer, we're going to have a compressor that's working in the back, and that compressor is going to be generating heat as it works to push the freon through as the freon evaporates, and look at all those different processes. And what's going to happen overall, if we look at the system and the surroundings and look at the entropy total of the whole everything, the entropy of the universe always increases. Some of the energy is going into useful or useless heat. The one thing that we know for sure is that the entropy of the universe will be greater tomorrow than it is today. Entropy is constantly increasing. As a matter of fact, some propose that time itself is linked to this increase in entropy. For instance, you take a ball, you videotape a ball being dropped off a tower. Well, the ball's going to drop, and when it hits the ground, some of the energy is going to be translated into vibration, noise of the air as it bounces around. Some is going to be frictional loss to heat to the surroundings as it hits the ground. The ground itself is going to vibrate a little bit. As a result, the ball doesn't bounce as high on the bounce. And then the same thing repeats itself when it bounces again, until finally all the energy, the potential energy that it had up on the tower, is now dissipated into this vibratory motion, this useless heat that's going out throughout all the places. So we know that looking at that, the ball bouncing, we know that time is going forwards. If somehow we put it in reverse, we started seeing the ball going higher and higher and higher, we know that, oh, we must be going backwards in time because the ball is getting higher and entropy is actually decreasing all the way up. Now, some scientists hypothesize that the universe is expanding. They're not hypothesizing saying that, but at some point it's going to stop, and then it's going to begin coming back together again. That gravity eventually is going to grab hold of it, and it's going to start coming back together. Now, recently they've come out and found that the universe actually isn't slowing down. It's actually speeding up. They don't really have an explanation as to why it's doing that. But some were saying that it could possibly, gravity could stop us, pull us back in. And if it pulls us back in, entropy then, instead of always increasing, entropy is going to begin to decrease. What does that mean then about time? The time would be going backwards. Okay? So then we'd be coming back. So then the ball, instead of bouncing down, 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 then the ball would start going back, back, up, 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 up. Okay? So you'd have two chances to mess up history. Kind of, going forwards, and then you'd have another chance as you're coming back and going time in reverse. Possibly life is one big loop of out and back. Maybe this is what reincarnation is all about. Maybe, it's just when it comes back, and then you go back, and then go back again. It's just one big billion-year, multi-billion-year loop of back and forth. Just something to think. Not just for the record, I don't believe any of that, but it is just something to think about. It's kind of crazy. Now, what was your question? I spoiled the moment. I'm so sorry. Okay? But entropy measures chaos. We know that the entropy of the universe is constantly increasing. The entropy of an individual system can increase or decrease. Okay? Now, nature does favor the increase. Nature wants it to increase, but it can decrease. But the entropy of the universe, S of the universe, is always increasing. The entropy of the universe is always increasing.
You mean like the universe is like a whole?
Yes.
Just like all
the universe is the system and surroundings combined. Okay? So whenever we combine system plus surroundings, we equal universe. Now, we can calculate quantitatively the entropy, delta S of a reaction, and again, remember the degrees means standard state. Delta S of a reaction, this is going to look familiar, is equal to the S of formation of products minus the sum of S of formation of reactants. This is on the same table, page 1122 in the back of your book that we use for delta H. Okay? So we do and solve this the exact same way. But we can qualitatively measure entropy by just looking at the gaseous products and the gaseous reactants. When the moles of gaseous products is greater than the moles of gaseous reactants, entropy increases. Okay? Now, obviously, the reverse of that is true.
So
Not necessarily. It has to do with more of the state of matter than it does what it's bonded to or with. Okay? So delta H and delta S are really independent of one another, but hopefully in the next couple of minutes I'm going to relate the two together. Okay? So we can do qualitatively or we can do quantitatively. Quantitatively is going to be just like our delta H. We're just going to plug in the values just like we did before Christmas with the delta H. We just change and we look on the exact same page. We just pick out entropy, the delta S values versus the delta H values. So, but let's look at how to do this qualitatively. If you get your white book out and turn to page 839. 839. Y'all, 15 minutes. You can do it. Make it through another Thursday. Just thank God it's not history or English. Wrong answer, Rizwan. You're supposed to say yeah. Okay, looking on page 839, let's look at number 37 and just kind of compare. Now, just talking, what do you think has got more chaos, a solid, liquid, or a gas? Gas. Okay. What do you think is going to have more chaos, a solid, say water, let's say water at 0 degrees or water at 95 degrees? Why? Because the molecules are moving faster. Okay. What about is that my phone? Yeah. What about sugar as a solid or sugar dissolved in water? Sugar dissolved in water because there's going to be more randomness, more chaos. In the solid state, it's in that orderly crystal lattice structure, okay? But then you put it into water, then it breaks apart, you get much more randomness. Now here's one. What about CO2 gas, the carbonation, the fizz and pop? You put CO2 gas into water. Which one's going to be CO2 gas by itself or CO2 in water is going to have a higher entropy? Okay, why CO2 gas? Exactly right. No restricts it. You can go anywhere. It can spread out to fill any room, whereas in the liquid, when you dissolve it, it's much more confined. Okay? So let's look at some of these then and just kind of compare on 39. It says argon liquid or argon gas. We're just going to have the higher entropy. Okay? The gas. Helium gas at 3 atmospheres or helium gas at 1.5 atmospheres? What'd you say? Okay, I got 1.5, we got 3. How many of y'all think it's 1.5? How many think it's 3? Okay? Let's defend 3. I heard a defense of 1.5. No, well, no, I've already heard that defense. What was your defense of 1.5? Okay, it's not as constrained in the small area. It's more spread out. What's the argument for 3? It has more collisions. Okay? The answer is, okay, 1.5. The more spread out it is, the more random it's going to be. The closer you put them in, the more compact they're... Seriously? Okay? Yeah. Okay? So, it's going to be... I do need to check it. It's 1.5 because... Oh, it's nobody. $1.5 because it's going to be more spread out. The more spread out a gas is, the more higher the entropy is going to be. So then the next one is going to be 1 mole neon in 15 liters and 1 mole neon in 1.5 liters. So which one, based on the same premise? 15 liters. More spread out, more randomness. And then lastly, CO2 gas or CO2 solid gas. Now for the sake of time, let's look at 38. Here's a good one. P4 gas at 300 or 1 mole of AS4 at 300. So they're all at the same conditions of temperature and pressure. It's just P4 versus AS4. Okay, why P4? So would that have more chaos? Higher molecular speed. Okay, but what about the size of the electron clouds? And the chaos inside the electron clouds themselves. Bigger molecules are going to have higher entropies. So if you're going to compare neon, helium, neon, argon, krypton, xenon, radon, they're all monatomic atoms. So they're just floating around as single atoms. Radon is going to have the highest entropy because the electron cloud is biggest, and you're just going to have the most entropy even just within the atom itself. So if everything's the same, the bigger the molecule, then the higher the entropy. Now, balance that with the next one, though, down, or maybe 2 down, where it compares nitrogen gas, N2, to CH4. N2 to CH4. Now, if we just went with N2 with a molar mass of 28 versus CH4 molar mass of 16, we'd be tempted to say N2. But CH4 has 5 atoms attached to it. There's the carbon with 4 hydrogens attached. So there's more atoms. So there's going to be more vibratory motion, more everything, more chaos there than there is in an N2, where it's the same atom bonded together. Okay? So the greater number of atoms is going to... notice the difference between that one and P4 and AS4. Everything is the same on that one. Then it's the size makes the difference. Okay? And then lastly, Na2SO4 solid or Na2SO4 aqueous. Aqueous. Okay? Now, looking at 39, we want to apply this principle. 39 says SO2 gas plus O2 gas goes to 2SO3. What do we know about moles of gas to... how many reactant moles of gas and how many product moles of gas do we have? 3 to 2. So moles of gas is decreasing, so what's happening to entropy? It's decreasing as well. So the sign is going to be negative. Whereas BaOH2 solid going to BaO solid and H2O gas is 0 moles of gas to 1 mole of gas, so it's increasing. Now you only look at gas on these. So C, CO gas plus 2H2 gas, you got 3 moles of gas going to 1 mole of liquid. So what's happening to entropy? It's decreasing. It's a negative delta S. And then lastly, D, FeCl2 plus H2, well, you got 1 mole of gas going to 2 moles of gas. It's going to increase. Okay? So now move down to 47. And let's just do this qualitatively. Okay? That was 39. Look at 47A. Take 10 seconds. Is the delta S going to be positive or negative? Negative. Okay? Don't say an answer out now. Look at B. So 47B, what do we think? Why positive? You go in 1 mole to 2 moles. 1 mole of gaseous reactant to 2 moles, and that's your explanation. What about C? Positive, because you're going from how many to how many? 0 to 1. And then lastly on D? Okay, positive, because you're going from 5 to 6, right? And then you only look at moles of gas on that one. So you just, how does the moles of gas change? So we can qualitatively, and these are multiple choice questions. These are easy money multiple choice questions on the AP test as far as predicting the sign of given 4 different equations. Okay? Now, hang in there with me. Last thing we need to do is on 47D, I want you to go through and use the back of the book and calculate the actual quantitative delta S. Okay? Calculate delta S. And unfortunately, we're going to get done with that. We're going to be about 10 to 15 minutes behind the other class. Okay? So we just didn't quite get to delta G, the last thing, and that's about 10 to 15 minutes left of this chapter. I'll finish that up tomorrow, and then we'll just start practice problems tomorrow. Okay? But let's try to get 47D with just doing this. Products minus reactants. Use an 1122 at the back of the book. And the answer's in the back of the book too, so you can check yourself when you're done. Just D, 47D.